And we're back. Okay, so this one is a good one for anybody who wants to test themselves on the test related to variations. So direct variation, partial variation, sometimes we call it direct proportion and partial proportion, on the introduction of slope, how to calculate them, and then first difference and second difference. So I will put a link in the show notes, okay, so below, and that link is going to be this particular test that you see on the screen, and you can take it on your own. So before watching the video, give it a shot. Give yourself about 60 minutes to really test yourself to see if you understand it, and then you can come back and watch the solutions, all right, which I'm going to take up right now. All right, okay, so let's take a look at this thing. Okay, so I'm going to go kind of step by step and then walk through it and then make some comments on things that you should know. So these variations or proportions are definitely worthwhile knowing. You're going to run into them in sciences and in math if you carry on. Okay, so first question, what is the difference between a direct variation and a direct proportion? So a direct variation and a direct proportion. There is no difference at all, okay? It is just terminology. So some people call it a variation, some people call it a proportion. So remember that the structure of a direct variation or a direct proportion is y is equal to kx. So we have a relationship between the y and the x, and this k right here is our constant of proportionality or constant of variation, okay? And it is just some number which we call k. So there is no difference at all right, in here. Question number 2. Let's scroll down here. Let's take a look. What is the difference between a direct variation and a partial variation? All right, so this one is a little bit different. So we do have, I'll give maybe a little bit more than I should, but here we go. So as I said, so a direct variation, so we have y is equal to kx, okay, in this particular format. And partial variation is actually y is equal to kx. So this is the variation itself. Now, what we do is, okay, we're going to have, so some change, some partial shift, okay, in the actual variation itself. So we have this additional constant term, okay, sometimes we just call it b, which would be your y-intercept throughout. Visually, if you want to be able to see what the difference is, and you should know this, so if you're going to be taking a look, okay, so let's say I have, so here I'm just going to draw kind of a little coordinate system here, okay? So we have this coordinate system. Now y is equal to kx. So if you were graphing that, I'm going to do that one, I guess, maybe in pink. So depending how you graph it, it always goes through the origin, all right? So no matter what, okay, these lines always go through the origin. Now, depending the steepness of that slope, which is really this k, that's the slope right there, okay, so it will just make it more steep or less steep, but always goes through the origin. While, okay, if you're going to take this partial variation, because of the shift, this, okay, is not equal to 0. So we assume that it is not equal to 0. So what happens is, okay, that it gets shifted up or down. So it's not going to go necessarily through the origin. It might go kind of in this direction. All right, it might go at the bottom, so in this direction. Now, please don't think that the slopes are always positive and going this way. So you could, okay, have these lines. Let me erase them for us. Whoops, too much erasing. All right, so let me erase that. Okay, so they can definitely have a negative slope, and they would just be going downwards, all right, or rising to the upper left corner. And the same thing happens with the direct variation. So with this one, it doesn't always have to go through the origin rising to the right. It might rise in this way, okay, with something coming down. So that is the difference between the two, okay? Okay, question number 3. In your own words, explain what a negative slope of a line means. All right, I guess I kind of gave it away. So if you're going to take, let me erase this right here, and let me take this so it makes it a little bit easier for me. Bring it down. So if we take that, all right, so if I have this, okay, now negative slope means that it is going to be rising, okay, in this direction, so to the left. So the steepness is to the left. That's what a negative slope actually means. So it's rising to the left, or it is falling, okay, in this direction. So just depending on what kind of a line you have. So that's what the negative slope means. So negative slope means steepness rising to the left, or steepness, okay, falling to the right. All right, so that's what we have. Can you have a slope of 0? Of course you can have a slope of 0. So a slope of 0 just basically means that you have a flat line. Okay, so you would have some flat line. Now it doesn't matter where it is. It can be up on top, at the bottom, doesn't matter. But what it means is that the slope is 0. It's a horizontal line. All right, it's flat. All right, so now let's do question number 4. Okay, so we have, based on the table provided, state what is the constant of variation, what is the slope if you graph the table of values, and what is the second difference. Okay, so let's do that. First, okay, let's highlight these things so we don't forget. So constant of variation and the slope, those should be the same if this is a linear line. Now we're supposed to graph this as well, and then we're supposed to find the second difference. Okay, so I'm kind of going to go backwards, okay, because I'm seeing the second difference. Let's just check. So here, all right, so if I notice the difference between these, so from 3 to 6, 6 to 9, and 9 to 12, so the difference is actually 3. And if that happens in your independent variable, so your time variable in this case, then we can actually take the first difference. So now the first difference between this and this, all right, okay, so that would be, so if we subtract these two, so notice we're going to get 3.6 minus 1.8, which is 1.8. That's the first difference there. Now if we take, again, so we got to compare. So if I take the first difference between these, so again it's going to be, so 5.4 minus 3.6, so that's actually again 1.8. And then the last one, so the difference between these, 7.2 and 5.4, and that's also 1.8. So that's my first difference. Now they're asking me for the second difference. Well, the first difference is the same. So the second difference would be the subtraction between these two, which basically is 0, and then the subtraction between this is 0. So my second difference is equal to 0. So indeed, this is a line, if you remember. Okay, so that would be answering this part right there. Now let's try to graph it. I will cheat a little bit because I have kind of graphed it, just so that I'm not sketching it out and you're looking at it. So here is kind of a sketch of a graph. Let me put this and paste it back in here, so just so you can see it. All right, so that's the graph itself of all the points. So notice what I did was, so I have 3, 1.8, so that's this point right here, then 6, okay, and 3.6, 9, okay, and then so on. So those are my points. I know it's not perfectly graphed, but it's a sketch enough. And now what I've done is, because they want the slope, so the slope is, notice it's the rise over the run. So if I look at the rise over the run, and that's also going to be my constant of variation, right? So that's my constant of variation. So remember that constant of variation is basically your slope from the graph. So I have m equals, so my rise, So 7.2, so 7.2 and 1.8. So if I subtract this, so I have that. And then 12, my run, 12 minus 3. So this is going to be 5.4 divided by 9. And you can take out the calculator if you like. Now I know that 9 goes into 54, so 6 times, but it's 5.4. So my slope is actually 0.8. All right, so that's what it is. Now notice it is milliliters, okay, because that's the dependent variable, and then per, all right, minute. So that's actually my rate of change, which is 0.6. It's positive, so that's my slope that I have, and that is also my constant of variation. All right, so this is also your constant of variation. So this is your constant. So that's that K. All right, so that's what we would have. And I think that answers the question. So constant of variation, that is equal to your slope. And we've graphed it and we found the second difference. Perfect. Okay, so that was a great question. Okay, next question. If you would extrapolate the line in the previous question, then is it a direct proportion or a partial variation? Why? Well, if I extrapolate this, so what I have is, I guess I have to take the line and extrapolate. Well, this goes right through 0. So if it's going right through 0, it is basically a direct proportion, okay, or a direct variation. So that's what this would be. This is direct, and it says why? Well, because, okay, the line goes through the origin. So it has the format of y is equal to kx, or y is equal to m for its slope, right? X. So that's number 5. Let's take a look. Okay, so next one, provide 3 numeric examples from everyday life of unit rates. So this is just testing you if you understand the unit rates. So one example here, they give you $40 per hour, which is your hourly wage. Okay, so we can come up with 3 numeric ones. You can choose whichever ones you like. So I'll just kind of think of them arbitrarily. So for instance, okay, so 1 unit rate, which a lot of people know, is driving. So let's say if we were going 100 kilometers per hour, right? So this would be your speed. Okay, so that is the rate of speed. Notice it is a unit rate because it's per 1 hour. So that's one example. Another example I can think of is, for example, administering medication to a patient. So let's say maybe something like this, 20 milliliters, all right, per hour. Okay, so this is the rate of flow, okay, of your volume. So that would be a second one. So how quickly maybe a patient is receiving. So that is a unit rate. Again, it is per 1. Okay, and you know, another rate of change. So for example, maybe you're on a specific diet or something like that, and you're supposed to be consuming, let's say 1,500 calories. So 1,500 calories per day. All right, so that is another, okay, so rate. So this is rate of energy. Okay, and notice they're all unit rates because they're per 1. Now you can put anything else. I mean, you can certainly, so I mean, this money one was another one, but those are definitely 3 that you could have used. And I'm curious if somebody has something different, they can put it down in the comments. I'm curious what which one you came up with. Okay, question number 7. Complete the following table. State if the table represents a direct variation or a partial variation. So we're going to assume that it's linear. And provide the slope of the line and the equation relating y and x. Okay, and we want to put it in the format of y is equal to mx plus b. So your m is basically your constant of variation. Now we are missing things. So notice right here, So we don't have a y value here, here, and there. Okay, so we're missing those, so some y and an x value. Now, so how would I approach this? Well, I am given 2 points. So notice here, I'm given this point, and I'm given this point. All right. So now just from those 2 points, I can find out quite a lot. All right. And notice it's going 0, 1, and then we're missing something at 3, 4. So that could be a 2 there. So we can check that. But we have those 2 points. So since we know it's a line, so remember we can actually draw this in some way. Okay, so we can kind of think about it. We can definitely find the slope. Okay, so we can do that. So our slope m is equal to, so it is rise over run, and that is just from those 2 points that I have, which is your y2 minus y1 divided by x2 minus x1. Okay, so that would be y, which is 9 minus 3 all over. And this is going to be 4 minus 1. All right? So that's what? 6 over 3. Okay, so our slope is 2. Okay, so great. So that helps us a lot because now we know that our slope is 2. Okay, so if our slope is 2, so I can plot this. So if we draw this out, so let me draw it out since I have a lot of space here. So we have that. Looks like they're all positive, so I'll keep them positive here. All right. So this is my x, this is my y. So this is what I have. So we have that. Now, of course, this will depend if I've actually graphed this proportionally, because if I didn't, then it's going to be all screwed up. Okay, and I notice that I'm not graphing it properly because I have the spacing between here. All right, so as I'm going, it's not the same spacing as here. So this is going to look probably a little bit off. But, okay, what I can do is, because I know that the slope is 2, all right, so the slope is equal to 2, which is 2 over 1. So that's rise over run. Okay, so I have that. So I can use my slope to find my points. Okay, so notice I actually don't even have to graph this as much. Okay, let me clean this up a little bit. So I have my slope. So in order to fill this out, notice the slope is 2, and these guys are increasing by 1. All right, so this would have been 2 right here. Okay, and now since they're increasing by 1, okay, then the slope, notice that the slope from here to here is supposed to be 2. So that's your first difference. This is supposed to be 2. This is supposed to be 2, and the difference here is 2. So this has to be 1. And then this has to be 7. All right, so if you would have graphed this, it would have went through 0, 1. So it would have went through here. So as you can see, so this line actually would have been going in this, whoops. Okay, so somehow in this direction right there. Okay, that's how it would have been heading out. So let's see, what did they ask again? So, state if the table direct variation or partial. Well, it's definitely partial variation because it's not going through 0. All right, so it's going through, okay, 1. So I have, so my slope is 2, and then it's going through 1, which is your y-intercept. So that's right there. So that is your format of the line. It is a partial variation. And we have the slope, which is 2. So we've actually found everything. We didn't have to actually necessarily graph it. All right, but for visual sake, okay, so that was kind of neat. All right, okay, so that's question number 7. Let's move on. Question number 8. You are setting up an online mini store. You initially invest $500 in building an app for selling your product. You currently have only one product, so some hand cream, and the cost associated with creating the cream is $2 per cream. All right, what is the constant of variation? Okay, so for this one, so what do we have? We have some fixed cost of $500 that we're starting with. So that is basically, you haven't even created any creams and you've invested $500. So we know that. And then for every single cream, we're going to be paying $2. Okay, so our overall cost actually, so our overall cost is going to be equal to $500 initial cost plus $2 for every cream. And let's say, the creams are X. Now you can rewrite this, okay, if you want to make it look like our line. So notice this is in the format of y is equal to mx plus b. So this right here, so this 2, that's your constant of variation. So you can answer that. Is this a direct or partial? Where it's definitely partial because we have this initial cost. Okay, so that is partial variation. The equation, so well, we have the equation. So the equation is right here. And what would be the cost for 100 creams? Well, the cost for 100 creams, so this is 100 creams plus 500. So this would have been $200 plus $500, so the cost is $700. So that's actually a nice question. It's much shorter than the previous one. And notice it is an application, okay, of these variations or proportions. Okay, question number 9. Identify if the relation given is direct, partial, or neither. Okay, so if you're ever given this, always think back. Okay, so this is direct, right? They're going to be looking like this if it is partial. And if it doesn't look like that, then it's neither of these. So for instance, right away, I know that D, so this one, this is neither. I'll put N, this is neither. Now A, so this one A, so notice it says y is equal to negative 2x plus 2. So that looks like this. So this is partial. So sure, it has a negative slope. It just means that it's sloping downwards. So that's partial. B is direct. So A is equal to 1.5b. So that looks like this. So this one right here, this is direct. That's D. And then the last one, this one. So don't get fooled by this. Notice they've written it like this, so you might think that this is neither. But, okay, of course you can rewrite this as that. Okay, so that is the same thing, and that actually looks like partial, where it basically is, so your K is 1, which would be in front of your C, and then your intercept, your B, your shift is 3. So don't get fooled by that. This is also partial. This one right here is also partial. So that's that example. Another great one. All right, let's take a look. So next, what is the slope of each of the lines in the diagram? All right, so this is testing us in terms of our slope. We do have a grid, so it makes things a lot easier. So remember, in order to find the slope, you need rise over run. So right away, let's see, they're using the colors. So let's call this A. Well, A, the slope is 0. That is for sure because it's flat. So that, you can just say this is flat line. That would justify that. If I take the blue one, so remember I need kind of 2 points and to see rise over run. So I'm going to try to see, all right, so it looks like
this goes right through the axes. And then does it go anywhere else through? Well, this one definitely, okay, goes through right there. So I can find the rise. So the rise would be, okay, so this is from, so in this direction, right? So that's the rise, so it's going up. So it's positive slopes. Now let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 over the run. So that would be this direction. All right. And that is how many grids? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And that's your slope. All right. 9 over 13, you can't really reduce that. I mean, if you wanted to put it as a decimal, you could, but just leave it as it is. So that is your slope there, and it is positive. Okay. So now if I erase that, the next one, okay, which is kind of the pinkish one or the purplish one. All right, so we can go from here and then here. So again, so rise, so this would be in this direction. Okay, so how many grid points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12, it's going up. And this is going in this direction. So notice it's going to the left. 1, 2, 3, 4, 5. So it's negative 5. So your slope, and it is negative. Notice it's sloping towards the left or falling down, depending also how you count it. If you went in this direction, so like if you were counting in this direction, it would have been negative 12 as your rise, and then your run would have been in this direction. Okay, so that would have been 5. So it's still negative 12 over 5. So that's the slope for that one. All right. So now we should be comfortable with the slopes. Okay, and so here is another one. Calculate, so question 11, calculate the rate of change for ABC, convert to unit rates rounded to the 1. Okay, rate of change. What is the rate of change? So rate of change is a comparison how one quantity changes with respect to another. And in terms of rates of change here, so we have volume, okay, on the vertical and time on the horizontal. And rates of change are basically slopes. So we would have to find out what the slope is, okay, for all of these. So we're kind of doing exactly the same thing as in the previous question. Okay, so here for A, so what we have for A, so let's see, my rise, so my rate of change for A, so my rate, they're all positive, by the way. So it looks like they're all positive and they're going to get bigger. So my rise is 1, 2, so 2, whoops, I got to be careful here. Almost made the mistake. Notice they did label the axes. Okay, so 2 spots is actually 10 milliliters there. So it's 10 milliliters all over, and that is 4 hours. 4 hours. Now they want the unit rate, so we have to divide this out. So 10 divided by 4, so that's going to be 2.5 milliliters per hour. Now it's a unit rate, it's per 1. Okay, so that's that first one. Let's take a look next for B. So B, okay, so notice for B, let me change the color. So we're right here. And notice that it is, so it's going up 1, 2, 3, 4, 20, 25, 30. So notice these are basically 5s. So that would be 25. So for B, my rate is 25 milliliters all over. It's still 4. Okay, so 4 hours. All right. So again, so 25 divided by 4. So 6.25 milliliters per hour. That would be your unit rate for B. And then your last one, so that's all the way here. So notice this is, it's going to be 35. Let me change color. Okay, so that is 35, and then time between 2 and 3. So this is 2.5. All right, so it's going in half, 2.5. So for C, your rate is, we said, 35 milliliters all over 2.5 hours. And that, so 35 divided by 2.5 is 14. So this is 14 milliliters per hour as your unit rate. All right, so that would be this example right there. That's what you would have. All right. Okay, so that's another good one, and it tests your ability on unit rates and calculating them. Remember, unit rates have to be per 1. And so this, okay, so brings us, I guess, to the last question. So for this question we have, the following table provides the remaining amount of energy after usage. Okay, so you have time, so notice it says time 0. So 300 calories, then after an hour you have only 240, after 2 hours you have 180, so it is constantly going down, right? So it's using the energy, whatever this is. Given the table, determine if the relation is linear or nonlinear based on calculating the first difference. Okay, so we can calculate the difference because notice that the time changes only by 1. So now if I calculate the first difference here, so 300 minus 240 is 60. 240 minus 180 is also 60. So this is linear. All right, so we can assume that it is linear based on the first difference. So the first difference is 60 and it was increasing by 1, so that's also the slope. Now, if the usage would continue at the same rate of change, then how long would it take to deplete the energy? Well, so it looks like, so notice from the first difference, this is your slope M. So this is 60, right, calories, okay, and it is actually did it backwards here. So notice the first difference is actually minus 60. So let's be careful with that. And the reason why I say that, it's 240 minus 300, which is negative 60, and then 180 minus 240, which is minus 60. Okay, so we can just remove this. I'm going to remove this, delete. All right, so that's what we have. So it is linear, okay, so in my slope is negative 60, so that's negative 60 calories per hour, okay, so notice it's changing per hour there, so that's per hour. So how long will it take? Well, if we did this, so notice it's changing by negative 60, so the next one would have been 120, right, that's that. Okay, so that would have been 3 hours, okay, because notice the change of of 60. Then it would have been 60, so that's 4 hours. And then it would have been 0. And that's 5 hours. So it looks like it would take 5 hours to deplete, okay, this entire thing. And, you would be able to write that down if that was on your test. Okay, what is the slope? And the rate of change for this example. Okay, so there we go. I actually did the slope and the rate of change, and that comes out directly from your first difference, and that is the rate of change is negative 60 calories per hour. So that means we're depleting it by 60 calories. So, and what is the meaning? The meaning is you are depleting your energy by 60 calories every single hour. That's what you would have to put. All right, so a good test, okay, definitely test your ability on understanding your variations or proportions, partial or direct, and then understanding how to calculate slopes and tie it into rates of change. Okay, and don't forget about your first difference and even your second difference, which was tested on this. So thanks for watching. I hope you tested yourself. Let me know how you did in the comments. Okay, so cheers everybody. We'll see you in a future video. Bye.